Okay, so this is section 5.3, exponential functions. In order to be able to work with exponential functions, there are certain laws of exponents that we have to be aware of, and we have to actually internalize. In other words, when we see these, we have to know exactly what it is that we're looking at. And the 6 laws that we're going to look at are basically what to do with the exponents when a problem is multiplied or raised to another power, divided, subtracted, whatever. So in other words, if I have a base, we're going to call it a base of A, and our bases in exponential functions have to be positive. So we're going to say that base A or base B, whichever one I'm using, has to be a positive number. That when we are working with exponents, if I have A to the S power, that can be any exponent that I want it to be, positive or negative, and I multiply same base with a different exponent, or it actually can be the same exponent, but I've got the same base multiplied together, that the result of that is going to be that same base, but now with the exponents added together. So let me give you an example of what that looks like. Let's say that I have 3 to the 4th, and I'm multiplying that by 3 to the 5th. Now we know that 3 to the 4th is the same as 3 times 3 times 3 times 3. And we know that 3 to the 5th is 3 times 3 times 3 times 3 times 3. And if I'm multiplying those together, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So this is equal to 3 to the 9th power. But if we use this property where we can add S and T together, 4 plus 5 is equal to 9. So we just know anytime we have two bases that are the same, multiplied together, we can add the exponents. Another example, let's say I have 3 to the x times 3 to the 4th. I can rewrite that as 3 to the x plus 4 because I can add these two exponents together even though I don't know what x actually is. The other 5 properties, let's keep going through them. One of them is if I have a base raised to a power. If I raise that whole thing to another power, I can now multiply the exponents together. So that's equal to the A, base A, to the S times T. And the example of that would be 3 to the 4th power all squared. Because remember what this really means. It means I have 3 to the 4th times 3 to the 4th, which is 3 to the 8th. Now, we got that by backing up to the property before, but we could have also just simply multiplied 4 times 2 equals 3 to the 8th power. The next property, and let's go back for just a second. If I was dividing, let's say I had A to the S divided by A to the T, that would be equal to A to the S minus T. So just like when we're multiplying, we add the exponents. When we're dividing, we subtract the exponents. And if we're doing a power, we multiply the exponents. But if we're doing a root, we divide the exponents. So let's say that I have the square root of A to the 5th. Well, there's a little 2 out there that we know is hidden. This is equal to A to the 5th divided by 2. So just like you can multiply exponents, you can divide exponents. So this would be A to the 5 halves. Our next property says if I have 2 different bases and I have them raised to the same power, then that's equal to each individual base raised to that power. So let's say that I have 3 to the times 5 to the 2nd power. That's equal to 3 squared times 5 squared. Now that might actually be easier to find than 15 times 15 because I've got 3 squared is 9 times 5 squared is 25, and that together is 225. That's easier for me to multiply in my head maybe than 15 times 15. Our next property or law says that if I have a base of 1 and I raise it to a power, the answer will always be 1. Well, that's easy to look at. Let's say I have 1 to the 5th power. You know you're really just multiplying 1 times 1 times 1 times 1 times 1. That answer is just simply 1. Conversely, if I have anything to the 0 power, the answer is also 1. Now, that's a little harder to explain. So I'm going to have to ask you just to trust me on this one, that a to the 0 power is equal to the number 1. But I can demonstrate it by writing this. If I have x to the 5th divided by x to the 5th, well, we know that's equal to the number 1 because anything divided by itself is equal to 1. But let's back up with this idea that I could now subtract those exponents. S minus t. So let me do 5 minus 5. That would equal x to the 0 power, which is also equal to 1. So like I said, any number, no matter what it is, if I raise it to the 0 power, is equal to the number 1. The last law of exponents that we're going to work with is negative exponents. If I have a to the negative s power, I can rewrite that as the reciprocal of a, in other words, 1 over a, to the positive s power. And because of the properties it says that we would distribute here, this is 1 to the s and a to the s. 1 to the s is equal to just 1, and a to the s is right here. So let's take an example. Let's say that I had 3 to the negative 4th power. That's the same thing as writing 1/3, that's the reciprocal of 3, to the positive 4th power. Well, 1 to the 4th is 1, 3 to the 4th is 3 to the 4th, which you also happen to know is 81. So what this property does, it's very useful for, is it says that if I have any one of these forms and I want the other one, I can find it. So if I saw 1 over 5 squared, and I wanted to happen to make this a base of 5 for some reason, which we'll get to that later, I could rewrite that as 5, which is the reciprocal of 1/5, to the negative 2 power. And it becomes very, very useful later. So these 6 properties of exponents, or laws of exponents, are going to be incredibly useful throughout this unit. So you need to make sure that you know them, you internalize them. If you're multiplying with the same base, you can simply add the exponents. Or dividing with the same base, you can subtract the exponents. That's one property together. If you're taking a power, you can multiply them. If you're taking a root, you can divide. Same, that's the 2 different versions of the same law. That if you have an exponent of 2 different bases, you can split that exponent. 1 to any power is always 1. Anything to the 0 power is always 1. And a negative exponent means you can do a positive exponent of the reciprocal of the base. Okay, so now that we have our laws, let's do some exploration with exponential functions. Now, a couple things we need to know. Exponential functions have to be smooth and continuous. Exponential functions are going to be smooth and continuous. They can be graphed. And we're just going to do a little bit of example work with an exponential function that happens to be a growth. We're going to be introduction to exponential growth is what we are looking at here. Sorry, let me reset the light a little better. That might be helpful. Okay. I have a value function of f. I have a function of f, and it has 2 properties. The value of f will double every time it increases by 1. So in other words, every time my x value increases, my y value is going to double. The next thing that I know is that the first value, when x is 0, sometimes that's called the initial value of my particular problem is 5. So on my very first problem, I have a y value of 5. Now, I want you to notice that if I'm doubling it, what am I doing to it? I'm multiplying it by 2. So here is my initial value, and I am going to multiply that by 2. That becomes 10. Now I'm going to double that again. So I'm going to take that value, which we had as 5 times 2, and we're going to multiply that by 2 again. Now we're going to take the next one, and we're going to multiply by 2 again. And we're going to double one more time, times 2, times 2, times 2, times 2 again, which is 80. Well, let's just multiply what this is. This is 5. This is 5 times 2, 5 times 2 times 2, 5 times 2 times 2 times 2. And let's write that in exponent form. Now I'm going to skip that first one for just a minute. We'll come back to it. This is 5 times 2 to the first power. This is 5 times 2 squared. 5 times 2 to the third power. 5 times 2 to the fourth power. And if you go back and look at my exponents match. 1 is to the first power, 2 to the second, 3 to the third, 4 to the fourth. So when this one was 0, isn't that 5 times 2 to the 0 power? Because 2 to the 0 power, we've already proven, is 1. And so 5 times 1 is 5. Now, why did we do a process step? Well, when we look at this, what if I wanted the nth term? Well, if it was the 5th term, we would change that number to 5. If this was the 7th term, we would change that number to 7. But because it's the nth term, we're going to be multiplying 5 times 2 to the nth power. And ladies and gentlemen, that is an exponential growth problem. And it's written in this format: C times A to the x power. F of x equals C times A to the x power. The C right here, this C right here, is always going to be our initial value when x equals 0. Whatever that number is, that's going to be our initial value when x equals 0. The A right here is our growth factor. And if you looked at our original problem, what was the growth factor? Well, it was doubling. So it was growing at a rate of times 2. So our initial value when x is 0 is the C right there in the front of the equation. And the growth value, the growth factor, is A. Now there's some rules we have to follow. A has to be positive. We know that we're not going to have a growth when we have less than, or when our A value is negative. Okay, we're gonna have a function that kind of, if A was negative, we'd have a function that kind of, zoom out a little bit, kind of plots all over the place. We would have a positive number, then a negative number, then a positive number, and then a negative number. And there's no way to connect that into a smooth and continuous graph without any harsh terms. So we know that A has to be positive. We know it can't be 1, because 1 to any power would just be 1. And we know that C can't be 0, because if we multiply 0 by anything, then we have just 0 again. So we're going to know that C is our initial value whenever x is 0, and A is our growth factor. Well, what do we do with that information now that we know what that is? Well, let's take some tables of value. Let's look here at these tables of value. These tables are just data. But when you look at these tables, they can either be linear, exponential, or something else. And we'll just call it neither. It could be something else. It could be quadratic or whatever. But we're going to say neither right now because it's not linear and it's not exponential. If we find a linear table, we know that we're going to have the equation y equals mx plus b, which means that the b value would be our initial value and the m would be our slope. And of course, if we're finding an exponential model, it's going to fit the pattern CA to the x power. Well, how do I know what I'm looking at? Well, looking at this table, see if you can recognize that there is a change from 5 to 2. How can I get from 5 to 2? Well, I could multiply by 2/5, but if I multiplied 2 times 2/5, it's not going to give me -1. Or I can simply subtract 3 over and over and over again. That's called a constant rate of change. And a constant rate of change is called a slope. The change in y over the change in x, which here was just 1 each time, was a constant rate of change. That's our slope. So the equation for this first table is y equals -3x, and my initial value is right there, plus 2. We know that we have a linear equation in this table of data. This next problem, I could do 32 minus 16 is 16, but then 16 minus 16 is not 8. So let's look and see if there is a constant multiplier. 32 times what would be 16? 32 times 1/2 is equal to 16. 16 times 1/2 is 8. 8 times 1/2 is 4. 4 times 1/2 is 2. We do have a constant multiplier. Our growth factor, our growth multiplier is 1/2. Where do we find our initial value? Right there. So this has a constant growth factor, meaning that we're multiplying by something, of 1/2 to the x power, and it has an initial value of 16. So our equation for this problem is y equals 16 times 1/2 to the x power. Let's take a look at this last one right here. We have plus 2 or times 2, whichever one. But then the next one is not times 2 and it's not plus 2 either. It's actually plus 3 and then plus 4 and then plus 5. That means that this is not a constant growth like the linear was, and it's not a constant multiplier like the exponential was. That means that this particular function is neither linear nor exponential.